All right, thank you everybody for coming. My name is Dimitri. I'm the co-organizer of the Meetup. Thank you, Google, for hosting, and thank you to our presenters. We'll have Rain speaking about
hash tables.
Hash tables, that's right. And then Jacob will talk about atomic slot migration. If you guys are interested, please come talk to me about potential future presentation. We love presenters. Otherwise, this would be a very boring event. We would just eat pizza and talk. Also, we had an idea recently about potentially doing a hackathon, some like a weekend event. You know, people show up and they build something and they have to present it, let's say 5 o'clock on Sunday. So if anybody is interested in participating in that or contributing in other ways, talk to me. We have absolutely no planning done so far, but we are basically thinking of working with a local large technology company who might be willing to donate some space and pizza or whatever, and then people just show up with their laptops and build stuff and then present. All right. We hope to do another event early next year. It may be this hackathon event, maybe other presentations. So I will turn it over to the first presenter.
So these course to trip over. Okay, I'm going to talk about hash table, which replaced dict as our main hash table data structure in Valkey. So who to blame for this? It's me and Victor. We're the two culprits behind it. Victor is an open source developer based out of Sweden. Works for Ericsson. I work for AWS. I'm here in Seattle. I have 2 cats, too many hobbies. I could do things like I made the shield. It's kind of cool. I don't have much time. I'm sort of squishing this all in. So an overview first. I'm going to cover some background topics. We're going to refresh our minds on some computer science topics, data structures, computer architecture, and that'll set the scene for us to get into the hash table mechanics. Before we get into that, though, I'm going to be going through the review pretty fast, so hopefully I can just sort of jog your memory, you'll remember it. It's not going to be a proper explanation. Hold your questions until the end. I'm going to have an intermission in the middle for questions before we jump right into hash table itself. And I'm going to simplify a lot, but correct me if I say something that's like straight up wrong. Okay, so there's a few things we need to remember for Valkey that sort of inform what kind of hash table it needs. First, we pause resizing, or called rehashing, during BG save. When we call fork, there's 2 processes. This reduces the copy on write memory overhead. And of course, resizing has a lot of copy on write that it would cause. The second one, our items are different sizes, so we can't store them in a uniform array. And the third is we care about latency a lot. So like if a latency spike happened, we wouldn't be happy. Okay, data structures. What is a hash table? So famously, O of 1 time complexity on average. So you think of an array, and instead of doing a linear search to get through it, you have a hash function to know exactly which index to go to. Now, what do you do when 2 things hash to the same index? You need a strategy. The 2 main ones are chaining and open addressing. So chaining means you make a singly linked list at that index for all the things that hash to that index. If you want to find something there, you have to go through the whole list. Because of some math magic, it's still O of 1 time complexity on average. For open addressing, instead of storing it at that slot, you store it at the next slot in the array. So no linked lists, you just store it at the next one in the array, and then the next one if that one is full. So if you're searching for an item, you have to keep searching until you find an empty one. Now, what happens if you take something out of the middle? You need to know to keep continuing, so you need to have a system of markers and tombstones, things like that. So it's a little more complicated. Resizing, how do you do it? You make another one and you transfer everything over. Easy as that. Now, when to resize, you use a load factor threshold. That's item count divided by the size of your array. If it's too high, then your linked lists or your probe sequences start to get longer, and your time complexity starts to turn into O of n, or linear time. If it's too low, then you've just got tons of wasted space. And that's just something that you have to tune. There's no one correct answer necessarily. Computer architecture, cache levels. So the CPU works on registers. That's where it does the actual math and instructions. And you have a series of caches. Each one's bigger but slower than one below it until you get to main memory, which is where all of Valkey's information is. Each one is slower. This is a rough idea of the latency cost of doing a cache miss to that level. So light, famously fastest thing in the universe, travels about 1 foot in 1 nanosecond. So if you had a CPU going 5 gigahertz, light would travel about this far when you access a register. It would travel about this far to access L1 cache. It travel about 12 meters, like me to the middle of the room maybe, to access L3. For RAM, it's the back of the room. And for a solid state drive, I'm home already. It's 4.5 kilometers. So that's why Valkey exists. So a bit more about that. Cache lines. Memory is retrieved in cache line chunks, 64 bytes at a time. It's usually 64 bytes. This means that retrieving 1 byte is the same cost as retrieving 64 bytes. If you need more than 64 bytes, you have to do 2 fetches. There's other architectures like 32-bit uses 32-byte ones usually. There's some uncommon platforms that might use 128 bytes, but we're going to assume 64 bytes. It's the most common. CPU also has a prefetcher. Its job is to guess the memory you need next before you need it. And if it's successful, you don't have to pay any of those latency costs. It's just already there. So it really likes linear memory access. It's very predictable and knows exactly what you'll need next. So that's going linearly through memory. Random access, of course, hard to guess. Linked lists are especially tricky for a prefetcher. So there's no spatial locality. They're all different addresses. And the next address you need, you don't know until you fetch the previous one. So this is called pointer chasing. Also worth noting that there are software prefetchers, and you can do your own prefetching. Valkey does have its own prefetching algorithms, which I'll touch on later. Okay, going pretty fast. SIMD. Normally you think of like single instruction, single data, like take A and B, add them together and put that in C. With SIMD, you can take vectors like this, like maybe 16 values and 16 values, compare them all at once and put them in another vector, and that takes a single clock cycle. Or maybe a few. It's as fast as a single scalar instruction. So to stretch my light analogy a little bit more, with this, you'd get a comparison done in 38 light millimeters, so like that much. So it's fast if you can use it. Okay, so that's all the college review covered really, really fast. Now I'm going to get into some background about Valkey, some of our existing data structures before we started. So we use the J-malloc allocator. The main thing to know here, there's some good reasons that we use it, but the main thing to know here is that allocations come in discrete sizes. So if you ask for something that's in between sizes, it gets rounded up. Anytime you store something inside Valkey, it goes into an R object. It's just a ref counted server object that's pretty general. There's some metadata, and we've got a ref count and then a pointer to the actual data for your item. Before we did hash table, what we had was a struct called dict, and each entry in its array was one of these. You can see the code here. That's simplified it a little, but you have a key pointer, a value pointer, and a next pointer because it uses chaining to resolve collisions. So if you're storing like set foo bar sort of a thing, key would point to your foo key string, and then you'd point to an R object, and that would point to your value string here. So inside a dict might look a little bit like this. So this is a section maybe of your hash table array. And if you have 3 items here that collide at the same index, they would be chained together as a singly linked list. We don't rehash all at once because we don't like latency spikes, so we do incremental rehashing. The way that works is we do it step by step. So while we're rehashing, we have 2 hash tables. We've got the new one at the new size, and we've got the old one. And we go through and we take one of these lines at a time, each step, and move it over to the new table. And that avoids a big latency spike. Now, what if we want to look up an item that's here? Well, it's going to look a little more like this. We've got pointers that point to other allocations. So if we're ultimately trying to get this value string in Valkey, how many fetches is it going to take? Well, the first one, we go right to that index. We fetch that dict entry. Now we need to compare the string, so we have to fetch that. It wasn't the right one, so we need to fetch the next dict entry. Now we need to fetch that key, compare it. Wasn't right yet. We fetch the next one. We get its key. We compare it. It matches this time. So then we get the R object, and then we get our value. So 8 fetches later, we've got our value. Okay, record time. We've covered all these topics really fast. Does anyone have any questions about those before I get into the hash table itself?
We have internal metrics regarding how many facts we have.
I don't think we have internal metrics. Not that I know of. You could, there are CPU counters you could use to count cache misses at all those different levels. So that would be useful to have. We don't have a direct metric for this.
We have some like length.
Hmm?
We have the metric for length of the tree.
I don't know that we have metrics for that either. We do have some tests that look at how long the linked lists get at different load factors, essentially. Of course, it's average. It's a sort of a random thing where you end up with that. Okay, so 8 fetches was a lot. Seems like we could improve on that. We ready to jump in? All right. So of course, the problem and also the opportunity is all those allocations mean that we have a lot of allocator calls. Each one takes some overhead. There we spend more bytes on pointers pointing all over the place. There's more random memory accesses, more chances to have a cache miss, cache latency. It's just sort of bad. And of course, J Malik is rounding up for each of those. So in 8.0, we did an improvement, not Victor and me. This is before we got to it. If we embed the key into the dict entry, we can save the pointer, although we do have 1 byte of overhead here. So we save 7 bytes per item for every single item. That's pretty good, but you know, what went a little further? So Victor and I started with this idea. There's a talk done by Google, or developed by Google, the talk by Matt Kuklandis, designing a fast, efficient, cache-friendly hash table step by step. It's a very good talk. It's like 2 hours long, so I recommend it. I'm not going to cover all that. Also, it's open source, an Abseil library. But the main points from it are they used open addressing. They call it linear probing. So that means their data is stored in a contiguous array. They do assume that every item is the same size, but that means you don't need a pointer to get to it. You already know exactly the memory address it's going to be. Also, that means linear memory access. The prefetcher loves you. You hardly have to wait at all for memory to show up. The next innovation is that they cache 7 bits of prefix for the hash. So you remember we had that, we were fetching all the keys and doing hash comparisons. They compare the first 7 bits, and if it doesn't match, they don't look it up at all. So that means about 128 times fewer unnecessary key comparisons. So 127 times out of 128, if it doesn't match, it's going to stop here comparing the prefix. And all of that allows them to save memory. So they tuned their load factor higher for longer probe chains. Oh yeah, and they also use SIMD, so they're comparing 8 with each instruction. They're comparing 8 prefixes. So they have long probe chains. They have higher load factor, and they also don't have overflow buckets. And all of that comes together for memory savings and performance savings. Fortunately, it didn't work perfectly for Valkey. There's a few problems. We have differently sized items, if you remember. So we can't use the flat version of Swiss table. We're stuck with pointers to our items. It doesn't have incremental rehashing. So that's a problem that we have to solve. And with open addressing, you can't delay rehashing indefinitely. So when we pause rehashing, Valkey's still taking commands. It's taking writes. The hash table can be growing that whole time. With the chaining hash table, you can just keep making those chains longer. You can get to 500% load factor even. With open addressing, as you get close to 100%, it turns linear and it just falls off a cliff, goes down in flames. So for variable item size, we're forced to have pointers, of course. So we did a few things to address this. We got rid of dict entry, so no more dict entries. Instead, we put the key into our object. And we also put expire value into our object. So then we also use the same bucket idea. So we group together 7 items at a time into a 64-byte bucket. Remember, that's the size of a cache line. So we fetch 64 bytes at a time, the same cost as 32 bytes. But that gets us metadata and hash prefixes for 7 items. This is what our bucket struct looks like. So the first byte, there's 1 bit for each item to say whether it's present or populated. And then we store 8 bits of hash prefix. So we cut that by 256 times with that 1 extra bit. And then we have the 8-byte pointer that we're sort of stuck with. And all of that adds up to exactly 64 bytes. It's really convenient. For incremental rehashing, we originally tried to do open addressing like Swiss table. There was a lot of sort of complicated problems with that. So Valkey, of course, has constant adds and deletes for its hash table. And that means that probe sequences tend to sort of incrementally grow and get a little longer and a little longer. The more, even if it stays about the same size, the probe sequences tend to sort of build up. And we didn't think of any easy way to fix that. So we're just, well, we'll just rehash in place. We'll just make a new hash table and copy everything over and everything will be clean there. So that's obviously not very good. Incremental rehashing plus scanning, Valkey has a scan command. That was complicated and difficult. So the scan command is used to iterate through everything in a set or everything in Valkey, like stepwise, so you don't block the server for a long period of time. But that means you have to find safe places to stop in your scan. And who knows what'll happen before you come back. But you still have to guarantee that you don't skip any items. So you have to find a spot where you can stop. You can't stop in the middle of a probe chain because if a rehash happens while the scan is paused, it could move things from in front of the beginning of the probe chain to the end of the probe chain, or the probe chain could get shorter, and then scan would miss things. So that was just a huge headache. And then also, there's the problem of pausing rehashing when we do during BG save. What are we going to do there? We're going to have like a fail safe where we force the rehash to happen anyway and have terrible memory overhead, and probably BG save is going to fail. So we just did chaining. We already know how to do it. Solve all of Valkey's problems with this. We just modified Dick's algorithm. And this makes it easier to defragment long chains. We don't have to deal with the probe sequences. Probe sequences, they can get layered on top of each other and mixed up. With chaining, they're all separate. It's much cleaner, the code's cleaner, and there was much less debating and arguing about it between us. We did lose some prefetcher friendliness because a linked list like that, of course, isn't so friendly for the prefetcher. The way we implemented it is we had 1 bit left over, and we use that to indicate that this is now a pointer. Instead of to an item, it points to the next bucket. So to reiterate, there's 8 bits here. 7 of them indicate presence for these, and the 8th one indicates whether there's a chained bucket attached. Okay. We did keep SIMD though. We get that. This is our actual SIMD code. That's x86 and ARM. Made it a lot faster. I mean, not a lot, but like any bit you can get at this point is great. Our object embedding. This looks the same. The only thing we did is we borrowed 2 bits out of ref counts. So we have flags here, has expire and has embed key. And that just indicates whether we've tacked on some embedded data at the end. We don't really need 32 bits of ref count anyway. That's a little crazy. So if we have it embedded, this is what the actual memory layout looks like. So what we gained from this, all this work, we made a mess for a lot of folks. A lot of things were sort of changed and annoying, but what we gained is fewer memory allocations, fewer fetches, better cache locality. Things are grouped together more. We've got better memory efficiency. We save about 15 bytes per item with this, and we've got better performance. So it's a point of comparison. To remember this, we had 8 fetches to get to the 3rd one. With hash table, it looks more like this. We have 3 items hashed to this index, but they're grouped together in this bucket. So let's see what happens, how many fetches we need to get to this value string. First fetch, we get this whole bucket. We compare the hash prefixes for the first 2. You'd have to be pretty unlucky to for that to match and still not be the one you're looking for. It does happen, but let's assume it doesn't. Probably it won't. So we compare the 3, and the one that matches is the 3rd. So we fetch that R object. Second fetch. With this fetch, we've already got the key. We can hash it, do our hash comparison. We find out it matches. And we follow our pointer, and with the 3rd fetch, we've got our actual value string. So we went from 8 fetches down to 3. So of course, that's going to be faster. This is a micro benchmark at different miss rates, comparing dict and hash table. So this is ignoring 99% of Valkey and only looking at those data structures. So the first one is a 0% miss. Every single thing it looks up actually exists in the table. Then we've got 50% miss and then 100% miss, where it's looking for things that don't actually exist in a table. Like there's data there, but what you're looking for isn't there. So the first one is a 40% performance improvement. When it's 50-50, it's a 25% improvement. And when it's checking for things that aren't actually there, it's about a 50% improvement. Of course, this is without prefetching though. So once you add in all the rest of Valkey, the prefetching algorithm we have, it's a little more complicated. So this is comparing Valkey 8.0 to 8.1. The ones that I want to brag about are over here where IO threads is set to 9 and pipelining is set to 4. Get, where it's finding everything, about 11% better. Set is, wait, that was 9% better. This one's 11% better. This one's kind of strangely flat, and that's because prefetching. At the time, our prefetching algorithm was optimized for no pipelining. So prefetching is doing its thing here. It's hiding all of that memory latency. So it's sort of a wash there. By the way, Victor recently approved our prefetching, so these numbers are better now. Should get Victor to do a talk. Memory efficiency. So when we embedded the key, we saved 7 bytes per item. We went from this line to this line. With hash table, we saved another 15 bytes, which gets us down to this green line. To explain the graph a little bit, I'm using 16-byte keys, and then the size of the value string varies. Oh, and the zigzag, that's because of J. Malik. It rounds up to the next size. So when you reach here, you just go 1 byte over the size threshold, and it rounds up the size. So in terms of percentages of overhead, this is really good. If you have a 16-byte key and 21-byte value, save 41%. 41% less overhead. Bigger ones here, it's around 15, 20%. Pretty good. So that's the real win we got. Prefetching sort of hid away our performance wins, but we still won in memory. But could we go further? So if you're a developer, you might be familiar with the embedded string encoding. So for embedded string, the value gets tacked on here. And in this situation, we have our object pointer that just points to over here in the same allocation. So, seems a little silly. What if we were to just do a little math instead? What if then we could just sort of take this and just push it over, save 8 bytes. It'd be great, delightful. So with that change, we get this much more improvement. This PR is still up. It'll probably get into Valkey 9.1, but yeah. Okay, I made it, 30 minutes. Any questions? Yeah.
Yeah, you mentioned that you got rid of some random access with the chaining and using the hash prefix.
Yeah.
Where do you fit that in 8 bytes to prevent the load?
So
Yeah.
the prefix, so these are hash buckets. The prefixes live here.
Oh, okay.
Yeah.
So how many bits do you get for each prefix?
8 bits.
8 bits.
Yeah. So that reduces those unnecessary fetches by 256 times on average.
If it's zeroed out, that means it doesn't exist.
We actually have a single bit in this byte. There's 1 bit per item that says whether it's present or not.
Okay, so the first byte is present or not, and usually
Yeah.
7 next bytes.
Yeah, exactly. And then each of the next 8-byte chunk, 7 8-byte chunks is the pointer. Yeah.
So we're changing the last element is pointing to the next.
Yeah. Yeah.
And then I'm guessing the prefix is just meaningless to that.
Yeah, it's wasted space.
Yeah.
But yeah, we only if we don't need that, we can actually use 7. We use it if there's 7 items. When you switch to 8 items, then you have 6 in this bucket and then 2 in the next bucket. Maybe I should have had a slide for that. Q?
Can you repeat the question so that?
Oh yeah, thank you. How often do we have chaining?
Yeah.
That's a good point. We did do some experiments. I don't have it ready to show you right now. On average, when we're right about to rehash to a bigger hash table, we have on average, I think, trying to remember the percentage. I think 90% are a single bucket, and then 10% have 2 buckets on average.
You only need one.
Yeah, on average. So it doesn't happen very often.
If you have chaining, one more patch. 4 patch.
Yeah. So if this were chained and we had like 8 items, we do 1 fetch, compare all the prefixes. Probably we don't have to do any other fetches. All the prefixes take care of it. Then we do a second, third, and fourth. Yeah.
And rehashing gets paused with BG save.
Yes. Rehashing still gets paused with BG save.
So that might be the change.
Yeah, that's right. So that does cause, while it's paused, the table just can continue to grow. So you can end up with longer chains in that situation. Yeah.
In this slide, are all of these in the same bucket? Are they all hashes that collide together, or they are all different keys?
Yeah. So all of these items that are sharing a bucket, they hash the same array index,
Okay.
but they are unique keys,
Yeah.
right?
Sure.
So we make sure that the bits we use to determine the array index are different than the bits of the hash we use to prefix here. So
And do you have an explanation for why there was a consistent drop in 8-set performance? Or is that just like,
was it here?
yeah, 8-set?
The test at the time, so the question is, why is there a drop in performance sometimes? It's within our error bars. The test wasn't very good at the time. Yeah.
Did you change?
Yeah.
Did you change the way you calculate the load factor? Or
I don't remember. I think we didn't tweak it dramatically. If we had done something closer to Swiss table, then we would have tweaked load factor more. But the question was, did we tweak a load factor? We didn't really. Maybe slightly. In the back, Venkat. So were we able, when we were trying to do open addressing, were we able to measure the performance gains? Not significantly. We were falling all over the problems. And we ended up on chaining before we really got good measurements on that. Any other questions? Yes.
For sync operation, you mentioned 128 bits registers.
Mhm.
And so was this simplification for the presentation, or you also have implementation for like a bigger registers for a newer platforms, or we just always go with 128?
Let's get past it. So the question is, for SIMD, do we have any specializations for other sizes of cache lines, like 128 bytes? For SIMD, we only implemented it for 64 bytes, practically speaking. We have some, we did specialize hash table for 32-byte platforms, which we support. We didn't do SIMD for that, but we changed our bucket size. We don't have any specialization for 128 bytes cache lines. Yeah.
Format, a modified format, what will be the older keys that will be grouping 8 items? There was a diagram where it said it had already a key, something key format or something.
Was that for hash table or dict?
Older packet format. Top one.
Are you talking about the top line there, the R object? Okay, so the question is, do we still use the R object format? Yes, we did modify it a little bit to embed some things, but otherwise our object is the same. Did that answer your question?
Yes. What would be the value of key or object? You're actually using a newer
Okay, the question is, what is the value of the key stored here? And that's the SDS format representation of just the customer string. So if I type set foo bar, then that would be SDS saying foo.
So our object is now variable sized.
Yes, our object is now variably sized with the embedding. But so that's a good point. Before we embedded this stuff, our object was a uniform size, and maybe we could have put that in a uniform array. But then we still would need the pointer to the separate value string. So in the end, the most efficient thing to do was embed things in our object. Should probably turn it over. So find me afterward, find me on Slack if you have any more questions. Thank you.
It was on the brand website. It was like a poppy gold. Hello, hello. I'm gonna go ahead and get started. So hello, everyone. My name is Jacob. I'm here on GCP. I've been working on Valkey open source for, I guess, a few years now. And I'm happy to present my first, I guess, like major feature to Valkey, which is atomic slot migration, which came out here in Valkey 9.0. So without further ado, I can go ahead and get started. I'm going to get started with, like Rain did, some background. So in Valkey, you know, you can run Valkey either in standalone mode or in cluster mode. And when you run it in cluster mode, the way that we decide where to route requests to depends on where the key hashes to, which it uses the CRC16 hash basically, and then picks a slot based off of that key. And so there's 16,000 slots in Valkey, and each slot gets assigned to a shard. And within that shard, there is a primary node and potentially many replicas. And so cluster clients become aware of the topology, and then they use this to inform how to route things throughout the node or throughout the cluster. So in this case, I'm showing a simple 3-shard cluster where we have node A, B, C, and node A owns about 5,000 slots, and so does node B and node C. So clients coming in, they hash their data, and then they pick a node, and then they send us that node, and ideally the topology hasn't changed, and the node accepts it. So the problem then comes what do we do when we want to add a 4th node? So we need to take some of those slots that were previously owned by A, B, and C and move them into a new node, D. And so we have this process called slot migration. Well, we still have this process called slot migration, but we previously were using what I guess we're calling legacy slot migration now. And so legacy slot migration involves first going to the old node, and you tell the old node, you first go to the new node and you tell it, hey, you're going to be importing this slot. And you say, you're going to be importing it from this other node. And then you go to the source node and you say the other side of the equation. You say, hey, you're going to be migrating some data to this target node. Now, once we've established this kind of logical state between the two nodes, you can go and iterate through all of the keys in the slot that you want to migrate. So we provide a command, cluster get keys in slot. You run this command and you say, I want to iterate over, say, 10 keys. And it gives you 10 random keys that are currently hosted by this node in that slot. Now, for each of those keys, you then go to the source node and you say, hey, I want you to take this key and migrate it. And the migrate command is, I guess, it's part of clustering, but technically you can use it to move data between any two nodes. And it basically takes the key, serializes the key, sends it over to the other node, and then the other node restores the key. And then it comes back to the primary node, or sorry, the source node, and then it deletes the key locally. And so you do this you can provide a batch of keys, but you do this for every batch of keys until the slot has no more data left in it. During that time, the data is kind of logically located on both of the nodes. Eventually, you call get keys in slot, and there's nothing left. And so what happens then is you go to the target and you say, hey, you now own the slot. And then you go back to the source node and you say, hey, that target now owns the slot. And supposing there was no issues in any of those steps, you've now migrated the slot. But overall, it kind of requires you to have either an operator, a control plane, or a Valkey CLI, which is like the open source control plane tool, to run through this state machine and move everything over in a speedy manner. Because there's a couple problems that happen when we're migrating things. So as I mentioned before, normally client requests are coming in and they're hashing and then they're picking a node. So they'll pick the source node. But some of the data might have already been moved over to the target node. So when a client comes in and it says, hey, I want some data, and the data is no longer served by the source node then needs to tell the client, hey, I actually don't own that. You need to also check with this other node. So the client then goes to the target node and it says, hey, do you have this key A? And if it does have it, it gets the value. But it also has to do this for every miss as well, right? Because there's no tracking state on the source node as to what has been transferred over. And same for sets, right? Any new set that comes in needs to go to the target node. So you end up with doubling your round trip time, basically. Your client first goes to the source node, and then it's going to get redirected to the target node. And like during the migration, you can maybe say like roughly half of your requests are going to get redirected. Another problem that happens is, again, when you have this kind of split state, now a client might want to do something operating on both of those keys, right? So a simple example is it just wants to do a batch get, a multi-get. So it wants to get both key A and key B. So what happens is that just can't be served. And this is also true for like mset and any of these kind of multi-key operation commands. If not all of them are served locally, we just have to return an error. And so we return an error that says try again. So effectively, those keys are just, or those operations are just totally broken. Third, and this one comes up a lot when you kind of start to manage Valkey at scale, is not all keys are the same size. And not all keys are even string values, right? Like a lot of keys are collections of values, like hashes or lists, and those can grow to be arbitrarily large sizes. And the protocol itself is you have to move everything key-wise. So you first move A over, right? And then you go to move this large key L, right? But this could be like a hash with millions of entries, right? It could be gigabytes. And there are limits to what nodes will accept in requests. Like each element within a request needs to be below a certain size. Otherwise we have problems with allocating infinite memory, right? So once it hits a certain size, we will just drop the request. And this leaves the operator kind of with a tough decision, which is like, what do I do with L? Do I just delete it and finish the migration and rebuild it later? Or do I try to force move it with like increasing the size? And this is kind of also, there's further issues. Once you fix the max bulk len on the target node and you let it accept that value, you also have problems with this large key needs to be serialized to a very large contiguous memory chunk sent over. And then on the target node, it needs to allocate this big memory chunk as well. That might be more memory than we can actually provision. We can run out of memory. And also, when you want to restore that key, like millions of hash elements, that can take actually seconds of time on the main thread. And during that time, we may be like unable to serve health probes. And this can actually cause failovers, like if you have a big key and then you kind of try to force it through. And then the bad thing is usually you have something retrying this. And so it'll just constantly kind of query of death, whatever it's sending it to. So very bad. And you basically play this game of like, okay, let me adjust limits over and over again until that large key gets over. Or maybe you can't fit it over there, and now you need to move things off of the target node to make it fit. There's also some other problems. It's pretty slow because, as I mentioned, we do it slot by slot. And for each slot, you're going in batches, right? And you can increase the batching, basically pipelining that you do to reduce like the number of round trips you need to do. But basically, you're making the operation longer based off of what the time is to communicate between wherever your operator is and where Valkey is. So like, this might be a millisecond of round trip time, which doesn't seem like a lot, but when you're doing like 3 to 4 shards, that's like 4,000 slots that you need to move. And each slot needs to do at least 4 operations and then 2 operations for every batch of keys. And it adds up. Like it could take minutes of time. And that's just minutes of time where we're in this kind of degraded state. And it's also true that, as I kind of mentioned and alluded to, it's really hard to, once you get into like a stuck state, like you found a large key or you can't fit it, you might need to figure out ways to force a migration through because you've gotten so far into the migration that it might be more risky to kind of undo it than it is to kind of force it through. So, you might be having like 1 key left in the slot. And if you want to undo that, you need to move everything back to the old node. And then only once you've moved everything back, can you kind of reverse that finalization and make the old node own it again. And so oftentimes you just kind of end up in the half migrated state and there's no rollback, right? And even worse, the slot might be too big to fit on either node at this point because we're still serving sets and stuff, so it could have grown. And if you're running at very high memory, it's possible that moving it backwards just doesn't work, right? So those are all the problems. So now I want to introduce atomic slot migration. I guess, does anybody have any questions before I go forward on the old slot migration? Nope. Cool. Okay, so I first want to start with, I guess, like a timeline of the feature atomic slot migration, because when I was looking at this, I realized the first issue that we filed for atomic slot migration in the then Redis repository was in 2022. And then, we kind of started working on the first draft of the design in early 2024. And then the first PR I sent out was in January of this year. And then now, we're finally launching in October. So this is a multi-year effort to kind of improve the slot migration experience. And I was very astonished to realize that this was 3 years ago when we first had the idea. So what exactly is atomic slot migration? So I'm going to walk through the process. The first thing we do, if you're familiar with replication, this will be very familiar. And also, I guess we talked about it in the context of like BG save. We create a child process, and the child process, when we create that, it's going to kind of do some magic in the Linux kernel and some accounting to ensure that our child process has a view of memory that's a snapshot in time of when we took that fork from the parent process. So we create this child process, and then this child process then iterates over all of the keys in whatever we're migrating. In this case, it could be 1 slot, but we also support many batches of slots at the same time. So that child process iterates and is doing a dump of this and sending it to the target node. So during this time, we'll find key A, send key A over. There's also, possibility that incoming requests are hitting the source node, right? And so during this time, we continue to serve those on the source node. And we just keep track of them by creating, a backlog of those commands that were executed. So we're keeping track of those. The snapshot's still going, and the snapshot completes, sends over key A and B. Now, once the snapshot's done, the source node knows that, okay, I have some incremental writes that I need to send over. So it then streams the backlog over to the target node. And so now everything is fully synced. The slot 123 is on both nodes, a copy of slot 123. And then we do an atomic handoff. As part of that, we need to ensure that no more writes are coming to the source node. So we actually do pause incoming writes on the source node temporarily, just to make sure that that full incremental backlog gets drained, right? So we might kind of start the process, get some incremental backlog, pause, flush it out completely, and then now once that's completely done, we can hand it over safely. And so the transfer is now complete. So I kind of wanted to walk through how this looks from a few different perspectives. The first being probably not the most important one, but one of the most important ones, which is the operator's perspective. So when you go to do the migration, instead of it being that kind of 7-layer process, now you have 2 steps. One is you call migrate slots. You give it a slots range. So as I mentioned, this can be any number of slots, and they can be contiguous or non-contiguous. And you give it a target node. Behind the scenes, it's going to start the process we just talked about. And then, during this time, the operator can pull it. It's an asynchronous operation. So they're sending get slot migrations. And in get slot migrations, they're going to see all the active slot migrations. And they can just kind of execute this once every second or so until they see that the operation is completed. And importantly, we also give the option to run cancel migrations. So like if at any point you realize, oh, my application's on fire because the slot migration is taking a long time and consuming resources or whatever, you can just call cancel migrations and easily undo the operation, which was a big pain point before. And then finally, if there's a failure or anything, we also have that rollback capability. So we roll back and then we tell in the get slot migrations, we're going to include some information about why the failure happened. And ideally, you could consume this programmatically and retry as needed. I think the most important is like, what does it look like to a cluster client? So I have 2 GIFs here. On the top here is what the topology looks like as we execute atomic slot migrations. So this is for a 3 to 4 shard scale out. As you can see, it's almost instantaneous, and each of the batches is moved in a single atomic handover, hence atomic slot migration. And then on the bottom one, you can see we're going slot by slot. In this case, there's not a lot of data in the slots, so they move pretty quickly. But still, you can kind of see it's going between these 2 nodes, and there's a constant, you can see the importing state appearing and disappearing throughout. And during that time, cluster clients are going to have to be talking to both of the nodes. So that's how it looks from the topology point of view. Here's how it looks from the end user application point of view. This is running a benchmark and running the migrations on both of them. I think probably the majority of the impact here is just because of how long that slot migration was taking before. Now we get to do it very quickly, and we consume resources to get that done quickly, and that causes a small drop. But it's much better than the previous QPS hit that I was seeing from the benchmarking tool. Finally, I could talk about how it looks from a Valkey node's point of view. So here we have the user on the left, the source node, the target node, and then the replica of the target node. So to kick things off, the user sends the migrate slots. And then we have this new command we implemented called cluster sync slots. I abbreviated it to sync slots here. This command is used for all of the internal handshaking and state machine navigation. So when we first create the slot migration, the source creates a connection to the target and sends this establish command, which is starts the cluster migration process. So target then starts tracking the command. And then importantly, we also send target replica the establish command as well. So one important thing you might have noticed if you're observant is that the target node and the source node both have the keys at the same time, right? And some commands actually do let you access things outside of an individual request, right? So normally, like if I run a get command, right? My get command will do the CRC hashing and we'll pick a node, right? And that's based on the topology. If for whatever reason I go to the wrong node, we can send back a redirection. So if I try to do a point lookup on a specific key and I go to the target node, before the migration is completed, the target will still send me that redirect, even though it has some keys for it. it's not even going to get past that initial check, right? The problem is that I can run something like, give me a scan of the entire database, or dump everything you have, or collect some stats about everything in the database. So we have this important kind of notion of like containing those importing keys. And we have to replicate that to replicas as well, so that replicas don't somehow expose those or break that containment. So the replica also is kind of tracking a very simplified state machine just to keep that importing state. And also on the point of the replica, so after we do this establishing, we then fork our child process and send the snapshot data. Since it's so one thing I didn't mention actually, the snapshot, we don't use RDB here because there's no concept of like pushing an RDB file to a node. I guess for context, there's two ways to kind of persist data in Valkey. One is RDB and one is AOF. RDB is like a full, I guess like proprietary serialization protocol, a Valkey specific serialization protocol that stores all the data in a pretty compact way, but it's binary, right? And then AOF is literally just a command log that you can replay. So trying to send the RDB, you run into some of the same challenges that we had before with moving per key things, right? Like you can't really finish processing something in the RDB file until you've encapsulated a whole key. There's some things we could do to improve it in the future, but right now, without totally breaking apart the RDB, it's somewhat difficult. So for simplicity and for the purpose of getting atomic slot migration out there, we use the AOF format, which does pretty good still. It's not as compact as the RDB, but the best part about it is that we can just send that same stream of data straight to the replica, and the replica can replay it as if it's part of the replication stream. And there's no real challenge of taking something coming from the source and then just relaying it to the replica. So once we've loaded the whole entire snapshot, we go to our next phase. There's an end of file notation that we send through the sync slots. That's because unlike RDB, AOF doesn't tell you how much data you're going to load. So we just send the whole thing, and then we put an end of file at the end. And then we go to the last part, which is the incremental transfer. So the target sends back, hey, I've got everything. I want you to pause yourself. So that's this request pause. From here, that's the signal from the source to start sending all of those changes it's been accumulating in the meantime. So it sends those over. Those are then easily replayed on the replica as well, because any of the incremental changes are in the same format as the replication backlog. So those just forward straight to the replica. And then once we've sent everything, we send another command that says, hey, now we are paused. So we pause all reads and writes at this point, and we go to the final step of the transfer. We send the paused, and then the target does a final round trip just to make sure everything stays paused and to refresh that pause. The thing is, the pause gets enqueued at the very back of the AOF, right? So this may be, gets appended to the end of the incremental changes. So it tries to flush out all the incremental changes and then flush out the pause command, right? So in order for it to, we might have sent the pause command many seconds before, and we're kind of delayed in this pipelining. So we do a final round trip just to make sure everything is still paused and ready to go. And then the source side then repauses itself. And then finally, once we've gotten the final okay to do the takeover, the target side performs the topology change. It bumps its epoch. It broadcasts that to the whole cluster. And eventually, the source node finds out. Not eventually, it should be very quickly because it's done in inline broadcast. And the source node finds out, unpauses itself, makes the topology change, marks the migration done, and cleans up the slots. And so that's where the whole atomic swap happens, is at that point in time. Now the operator, the end user, is going to be polling, and after this point, they will see the successful state and be able to move to their next migration. And I do have a demo I can show. I have pre-recorded a video, but I can try to do it live. Okay. Okay, so I've lost my SSH connection. Okay, here we go. Okay, so I have a simple monitoring tool here that I kind of vibe coded that shows us the state of the Valkey cluster. Let's see, and over here I have a I did set up the SSH session, but it died. I have a client machine that I have a bunch of benchmarks and stuff I can run. Let me reconnect over here. So I can go ahead and start a load test. I'm using memtier because I think from what I tested, it seems to handle the cluster topology changes better. But I could start running the load test. You can see the CPU usage is high. Let's see. Yes. Okay, and then I'm going to run a legacy scale out. So we could see we're moving each slot one by one here to the new node. And this is the Valkey CLI showing progress for each slot it moves. And we're going to go through each of the nodes in the cluster and move them to that new target node. I did pre-fill the cluster with 40 gigabytes of data. So we're moving about 10 gigabytes total here because we're going from 3 to 4 nodes. And yeah, 1/3 of that is coming from each of the different source nodes. We finished the migration from one node to another. We're on the second node. I think importantly, you can note like we're here moving about 5,000 keys per second. I guess I can give some more info on what machines I'm running here. This is running on Google Cloud C4 machines in US Central 1. So, and these are running in a zonally distributed fashion. So one node is in each of the zones of US Central 1. And then the client machine is also in US Central 1. One thing I did note is that, because we're doing so many round trips, where we put the client machine matters a lot. Like if I put this in the same zone, the migrations happen a lot quicker than if it's in like a different zone, because I think I calculated, you need like, we're moving 4,000 slots. So you need at least, some order of 4,000 different round trip times, which, with 1 millisecond delay is about 40 seconds. But it actually it ends up being many, like four or so round trips per each slot that we move. So from what I saw here, it takes a few minutes. We're at the very end here. Just gonna let it finish. And then it should print how long we took doing the migration. Per key batch, yeah. So I guess you need 2 round trips at the beginning, one to kind of set the slot into those importing and migrating states. Then 2 round trips, one is to get the keys, you get an arbitrary set of keys, and then a second round trip to run the migrate command on those. Behind the scenes, the inline is doing another round trip to the other node, right, to restore it. But the more that you batch, the better your performance will be. So that took about 2 minutes, 25 seconds to do the scale out. Let me restart I've got to increase the number of, let me restart the load test. Now I am going to run the atomic slot migration scale in, ASM scale. So this has a patch to Valkey CLI that I sent out as a pull request to support the atomic slot migration through the Valkey CLI. But yeah, let me go ahead and run the ASM scale in. and hopefully it doesn't catch on fire. So you can see we're migrating 1,300 slots here from one node to the other. And this is under load. And then now it finished that batch. Now it's going to the second batch. And you can see the keys don't change until everything is moved over. Then we see a big keys per second change. That's because we don't actually show the keys to the end user until it's all done. We're on the last batch here, and it's done. And that was 28 seconds. So over a 4x improvement on the actual latency. And most importantly, you could see that there's a lot less impact on the client side regarding how much QPS it can drive. There still is impact because we have to do something, but without having this whole asking redirect and many different topology changes that can cause topology change storms from the client side, by just doing it in that one batch, it gets a lot more efficient. So yeah, that was the demo. Does anybody have any questions? Lots of questions. I'll start here. Oh, I actually do have a microphone. Hello?
So if I understand this correctly, the keys are actually getting stored not in a shadow database to the side, but actually in the memory data store, right?
Yes. Well, yes and no, because so yes, it is not in anything different than where keys are normally stored, but it is in some ways kind of a shadow because it's an in-memory shadow, but because it's completely inaccessible, right? So the way that we've broken down the hash table after many refactorings is that each slot gets its own hash table, and because of that, we're able to very clearly isolate them at the slot level. So you can't access anything in a slot that isn't that you don't serve.
And so a couple of follow-ups for that. What happens in the case of a rollback, if you could talk about that a little bit? And then the other thing is, what happens if the source node dies? Can it resume or things like that?
So, okay, I'll start with the first one. The first question, oh, sorry, you have a mic, so I don't need to repeat. So the first thing was about how do we handle the rollback, right? So whenever, I guess there's a couple different failure scenarios that might happen, right? Like we establish this connection from the source node to the target node, right? The connection might break for some reason. So either that might manifest as an actual closed file descriptor, or it might be, we do have like a health check that we send back and forth. We use the sync slots command again, and it just says ACK, right? So they're constantly ACKing each other. And then there's already a protocol or a configuration in Redis and Valkey for replication timeout. So we reuse that to kind of, once the replication timeout, we haven't gotten to ACK in that long, we close the connection. So the main way that right now we don't formally communicate from one node to another a failure, we just close the connection and it doesn't get retried after that point. So then whenever the connection is closed, the migration, we have a signal on our end. We're installing event handlers for each of these file descriptors. So when they get moved to closed state, we get an event and we look and we see that it's closed and we handle that by killing the migration. So on the target side, we have to do some cleanup, right? So we will iterate through those, anything that was in that job, right? All the slots in that job. And we delete anything that was in those databases, in those hash tables. Basically turn the hash tables into empty, right? And then that's effectively our cleanup, right? It was never exposed to the user, so there's nothing else to clean up. We also do have some tracking state, like we set a bit on each of the, it's not a bit. We have like a tracking set for which hash tables are being importing, just to prevent them. This was for like the key containment thing. So when we're iterating over it, we'll skip any of those. Importantly, though, like when we send like a full sync, we actually do iterate over those importing things so that like replicas are ensured to have those contents. But yeah. So that was the first question. Can you remind me of the second one?
So is there any resume functionality? But I got that from the first answer.
So right now, no resume functionality, right? Although it's something we could incrementally add, right? So we already do tell the target replica about the migration, so it does know about it, right? And so in theory, like we could, through a failover or something, continue doing the migration from where we are. But I think the atomic slot migration for Valkey 9 was already quite a large amount of code. We wanted to snapshot the progress we had. So no, we don't continue through failovers or anything like that. And it's also quite easy for, well, I guess there's a question of like whether doing the automated failover is the right thing for everyone. Maybe they want to back off and let the cluster stabilize before continuing. So, there's some decisions to be made there, but pushing that to the operator felt like the right first step before adding more automation. Yeah.
I got a couple of quick questions. So first, in the case of like scaling out under memory pressure, is there use cases where like the old solution might be better because of the copy on write?
Yeah, totally. I mean, so right now, the old solution, like the way it works, right, is you kind of effectively open both nodes for business to serve like one continuous slot across those two nodes, right? So because of that, like, there's no overhead, like memory overhead associated with like tracking changes or anything. In this case, we have this, let me find it, the backlog that we need to track on the left side, right? That backlog does consume memory. We also have a child process, right? So that's a snapshot, using the Linux magic, it's doing copy on write on the memory pages themselves when they become dirty in the parent process, right? So yes, there is memory increase on the source node. There are cases where you could definitely trigger a failure on atomic slot migration that you couldn't trigger on the legacy solution. But I think what's most important is that like we're kind of collapsing slot migration into the same vector of problems that already exist with replication. And this primitive, we can definitely continue to improve, right? So those are both very common problems with replication. Like you get into these full sync loops where I try to load it, but then there's too many incremental writes, and now I'm no longer able to continue my full sync. I have to do another one, right? So yeah, it's definitely a problem. I think we have a couple of things in the pipeline in the open source for solving that problem. One being we're looking at a way to do this in a forkless manner, right? Essentially like using some kind of background thread and some bookkeeping to prevent us from needing to do the copy on write thing. And secondly, we've talked a little bit about it. There's no formal plan yet, but under situations like this, it makes sense to incorporate some server-side load shedding, right? So that we can finish those operations. So for example, if that replication backlog fills up to the configured size, it probably makes sense to defer some of the client writes until we can fit them into that replication backlog rather than killing the job that we've already spent 10 minutes trying to do, right? So, there's some stuff we can do there, but yeah, great question.
Thank you.
Yeah, could you briefly explain how does the atomic slot migration help with the multi-key operation from the client? Yeah.
So multi-key operation, right? Before, because the keys could be split across source and target, right? Any multi-key operation targeting keys that were in the split state couldn't be served at all, right? Because we didn't have the state locally to serve it, and we're not doing some kind of like coordination where we go to the other node and get the response and join it with ours or anything like that. The important thing to know about atomic slot migration is that slot 123 is never losing any data on the left side until we do this atomic handover, right? So it's still serving a complete state on the left side, right? So multi-key operations can be served just from that in-memory state that we have, right? Now, if you have a multi-key operation or any operation that comes in at the very end, like right before the handoff, you're going to get redirected because we'll do this pause, and then when you come back, you'll get redirected. So that's one retry you need to do, but it will work immediately because you'll be told, hey, go to this other node, and then it will work there. Does that answer?
Yeah, thank you.
Thank you.
So I wanted to ask about whether it makes sense to transmit the all the mutations that have been accumulated during the process of transmitting the slot immediately to the target. In a way, this reduces eventually the inavailability time, and also it is more likely that the target will have sufficient memory where it's not clear on the source.
So yeah, what you described is called dual channel replication. We actually do have that feature for the normal replication path. We didn't implement it yet for atomic slot migration, but it's actually I wouldn't say trivial, but it's a very easy incremental feature for us to implement at this point, given the parity between replication and this design, right? It definitely helps, right? Like you can send the replication backlog to the target node. There's also a second thing that's happening that's somewhat glossed over with all of the forking and stuff, which is that because we're not using like the dual channel primitive, the child process is actually streaming that whole snapshot through a pipe in the parent process. So the parent process owns the file descriptor to the target node this whole time. It never transfers a file descriptor to the child process, right? Because of that, like all the communication actually still goes through the parent process, and that accumulates some CPU overhead on the parent process as well. So those are the two things that dual channel helps with. One, you can send the replication backlog in advance of the snapshot finishing. And then two is the snapshot can actually just send straight, the child process sends straight to the target node because it's given ownership of the file descriptor. They could just talk to it directly.
Yeah.
But yeah, definitely something we should look at for 9.1. It would help.
Thank you.
Any downsides to doing
To dual channel?
Yeah.
I think the only downside is that it's new. So it's like there's some stability. But I don't think that I guess, no. Okay, well, actually, with replication, dual channel makes, there's basically no downside, right? Because you're sending it to the replica, right? And if the replica runs out of memory, you're actually kind of fine with that because it already didn't have the state. If you're sending it to the target node, probably the target node is like a new node that you're sending, like in the scale out case, you're sending data to, so it might have more memory available. But it is a primary node, right? And so if you're choosing between storing it on one primary versus the other, and if those run out of memory, you need to do a failover, and it's a much bigger customer impact, right? So I wouldn't say it's a downside, but you're just changing who dies, right?
Maybe say that the one downside without the control of sending data is that you might consume too many. Obviously, then
So yeah, just to repeat, my understanding was that the downside is, Yair was bringing up was that sending the replication backlog could use additional resources on the source node that I guess previously storing it in memory didn't use. But he was also saying, if we work on throttling, we can better conserve the resources on the source node, and that would also help.
So one question for me is that how the cutoff time is determined. Like if we have high traffic in the source node, will that impact the overall migration time?
Yeah, that's actually a great question. I did glaze over that a little bit here. So specifically asking about how do we know when we can pause and kind of stop the mutations on the left side so that the target node can catch up. Right now it's a configuration, which I don't think is like a great answer, but right now we configure by default, we will only send over, we will only pause when we've sent everything that we have in memory over the wire. So I mean, that's the time it hits the TCP stack in the source node. Once everything has been entered into the TCP stack on the source node, do we pause? Now, if you have a lot of write throughput, it might be the case that you never hit 0, right? I think the pattern that, or I guess like the intuition we have here is that, what is a replication backlog is, replication backlog is kind of the difference between how quickly the target side can process something versus how quickly the source side can process something, right? If the source is behind, the replication backlog if the source, the number of mutations happening on the source is less than what the target can handle, you will eventually kind of drain to 0, right? Now, if the number of mutations that are happening on the source are accumulating quicker than the target can process them, you'll start accumulating towards infinity. Now, you obviously have like things like sinusoidal load patterns and stuff like that. But generally, like the intuition we had was that, if we start growing, like if the write traffic is too high such that we're never going to finish the incremental streaming, we'll hit our limit and then we'll just give up, right? Ideally, like instead of hitting the limit and giving up, we do the throttling. And then we can kind of throttle until it hits 0 and then continue. But for now, this will represent as a failure for the slot migration, right?
Regarding the mutation commands which accumulates on the source during the slot migration, right? Do you have a limit in terms of how big that can grow to?
Yeah. The limit is So basically, behind the scenes, it's being stored in the output buffer for the other node. So there's a client that we create internally has an output buffer construct, and that output buffer is limited by the replication output buffer that you configure on the node. So
is it a new config that you introduced in Valkey, or is it not?
No, it's the same as the replication backlog.
Okay.
Although it is in addition to the replication backlog. So
it's a different buffer that's not in. Okay. How does it interact with the max memory? Say max memory is exceeded, but then that buffer limit is not exceeded, or vice versa. Like,
it depends, I guess, what you have configured for like client eviction and stuff, right? Because it's an output buffer, right? So you might have it set up such that like you have a max memory for clients, and then eventually, that is exhausted, and then you start killing connections, right? And you might select the connection for the slot migration to be killed. Otherwise, it's the normal processing, right? So if you hit a limit before your replication buffer is exhausted, then you hit the limit on memory, right? Not a great story for Valkey in general is like, you have a bunch of buffers to configure, and you have to play around with them to find the right. You can't make sure that all the buffers sum up to the size of your node, right? Because most of the time you end up needing to over allocate a lot, right? And so I think this is something we've talked about before, is like, how can we better dynamically adjust the memory such that like we're accumulating up to the maximum memory and then making decisions about what to do, but it's not something.
Yeah, because like in my opinion, this is a very different use case from replication, right? So maybe a separate config will make sense.
Yeah, I think.
So you can tune your slot migration machinery based on your setup, right? So
a different config might make sense. We usually bias towards like less configs, which is less API surface and less need to bump major versions. But so we can add a new config, right? Yeah. But then if we ever want to adjust that config, now we have to wait until a major version. So I think you're right though, that like making it a second config makes sense. We can definitely take that feedback. Yeah.
Okay. Thanks.
Yeah, so this was just about, you mentioned there is AOF that's used. Is there a way that could be swapped out with other implementations? I guess maybe also could you describe the AOF use case a little more?
So the main reason we chose AOF is mostly so that like it really simplifies things regarding like what to do on the replica side, right? Because now it's AOF is the same data encoding that we send in the replication stream, right? So now the target's job, the target primary, it can just forward everything as if it was just replication traffic straight to its replica, right? So it's pretty simple, right? Now, if you enter like a special like RDB loading state or something like this, right? Now you have some more protocol stuff to figure out, right? So an RDB file is basically a big serial blob of the database, right? I think it's easy enough to say like, hey, I'm going to send you this big RDB blob to the target primary and have the target primary enter a special state where it's like, okay, I'm going to buffer this and process it as much as I can. But then kind of pushing that to the replica requires you to set up, again, a separate kind of RDB loading channel. You could try to, like we had a small discussion about like, could we like load it in chunks and then send the chunks as like specific commands to like target replica or something. But you end up, like I said, you have to figure out the protocol. And for the first version, it wasn't, I guess, the difference between AOF and RDB is mostly an efficiency of like how much the bytes get serialized as. And the efficiency, it's a good, I don't know the numbers off the top of my head, but I know RDB is more compact, but I don't think it's enough that like there's no value in doing it without being able to support RDB. But definitely one of the things that we were looking at as a follow-up was like, how can we move to using RDB?
We're actually serializing the RDB format, right? And then sending them over.
No, we're sending over. So like the way that AOF rewrite works is you actually rewrite collections as subcommands, right? So I guess I didn't mention this.
The value is just a blob. Like
no, blob is not a blob. It's a command, yeah. So for example, for set, it might be sadd and then, a batch of elements in that set.
So you don't serialize the value and then send over a restore command.
No, well, because restore has its own problem, right? Like, like I said, a large data structure. When you dump it, it will dump into. It could potentially be a gigabyte big dump, right? And now you need to restore it, right? So instead of doing that, the AOF rewrite already rewrites each collection into batches of mutations on the collection, and so it actually works pretty easily where we just rewrite onto the connection, and then the other side loads it. Yeah.
I guess the one other advantage of using AOF is that if you do bulk compression on the AOF stream, you would not have to decompress it before you send it to the replica. You can do it in parallel. You just forward everything to the while you decompress it on the primary.
Oh yeah, we don't compress it now, but so the question, yeah. Yes, yeah. That's true. I guess you could also send a compressed RDB stream though, right? To the primary, and then that would forward it to the replica. It could work something like that. We don't do any compression right now as to the stream. So it's just the raw commands, right? Those are definitely incremental improvements we can make.
Yeah, so this is using AOF from the target primary to the target replica.
Sorry, what was those two words? AOF from.
This is using AOF from the target, from the source to target, but also to the replica as well.
Yes, yeah, it's the target to the target replica is literally just a replay of what the target is getting over the link. It actually, I don't show it here, but like for simplicity, we just send everything to the replica that comes in over the link. And it's actually pretty efficient because we send it to it we don't even process it. Like, so normally you run a command on a primary, it processes the command, executes the command, and then regenerates a command to replay on the replica based off at the very end of the command processing. So this is how we do stuff like if you run increment on a string or on an integer, we run that increment and then we actually replicate the result of that increment so that it's a deterministic operation. But instead of doing that, because it's an AOF stream, which AOF is guaranteed to be deterministic, we could actually just forward it at like the layer 4 layer, right? Like it's just a full TCP proxy, which is actually how we do like chaining replication. I think we have one back there, and then.
When do we do the deletes after migration? Do we delete after each slot we send to target, or?
Yeah, so the whole it depends on your batching, right? So I guess ultimately the operator gets to choose. So you could send a slot range that's just one slot, right? And do it slot by slot. Probably not the best way to do it because you end up making a lot of topology changes, and each of those requires clients to kind of refresh, and it adds a lot of instability. what I was showing in my demo was like batching all of the things that needed to move into one migration. But I guess it's a trade-off, right? Like, because the bigger the migration, the more time it might take to do, the more these backlogs and stuff that might accumulate, and the more likely it is that it could fail, right? But I guess the other aspect is that a failure will roll back cleanly and you could just try it again. So maybe like you might want to write like a control plane that tries with a big batch, and if that fails, tries with the half of that batch, and then kind of proceeds from there. Like,
let's say I'm sending 5 slots and 3 were migrated, and somehow the rest of the 2 got cancelled or like terminated.
Yeah, those would be 5 different calls to migrate slots. Yeah, so you would say, so basically you would make 5 calls to do slot 1, 2, 3, 4, 5, right? 5 different commands, 5 different operations. We do mostly support concurrent migration of slots. So like you could actually just send them all as concurrent migrations to let like part of them succeed and part of them fail. The only thing is that right now, we only do 1 snapshot at a time. So the snapshots get serialized, but everything else can be happening concurrently. Obviously, if you had a lot of snapshots, it would really explode the memory overhead. So we don't do that. But so you get 1 snapshot at a time, but otherwise you're allowed to start concurrent migrations. So depends how you orchestrate it as an operator. Like if I do 1 migration with 5 slots, that will atomically succeed or atomically fail. But if I start 5 migrations, each with 1 slot, those could be independent of each other.
Okay.
Can you?
Quick question.
Sure.
If I understood correctly, you have, you start the child process or the serialization process from the primary, right?
Yes.
So did you consider, because primaries usually are under like heavy CPU utilization, so did you consider starting from replica instead?
Definitely, I guess it's feasible, right? I'm trying to think about how it would look. I guess like the replica could send over the snapshot it has at a certain point in time. You would need to make sure that the replica and the primary talk about what offset that snapshot started at. The primary would still accumulate the writes, but the primary might have to also send some recently accumulated data. Like for example, if the lag is 1 second, it might need to also send 1 second of data. But it's definitely possible. We don't do that right now, but very possible. I guess we could also do this for replication too, right? Like if you add a replica to a shard, it's possible you could do the full sync from another replica and then get the difference between that full sync with the primary through like psync or something. But yeah, not an optimization we have yet.
Yeah, you can use the replication protocol for the last piece of
Exactly. Yeah. No, that's a great idea. I think it's definitely feasible to reduce load on the primary. Yeah.
Another thing is that what happens if automatic failover happens? So you started off primary, but now it's not primary, it's replica now.
So anytime there's a failover, we give up. I guess the only thing that is special in that case is if I'm a target primary, if I'm a target primary and I'm demoted to replica and I like reload or I find out, I have to kind of transfer the cleanup to my new primary, right? So the old replica knows about the migration, and so when the old replica is promoted, it does the cleanup, but the old primary doesn't immediately fail the migration in that case. The new primary has to. Only primaries fail the migrations so that way, because like replicas, if the replica were to clean up independent of the primary, it would desync, and that would be a big problem. So otherwise, it's just if the source fails, it's an easy failure because we just mark the migration failed and we stop continuing on it. The target is the hard one because it needs to do some cleanup. Yeah.
Okay, thank you.
All right, I think he's had a question for some time. Could you pass the mic over here? Well, it's for the people online and the recording.
A question regarding the CPU utilization bump. I noticed during the demo, the nodes under migration seems running to like around 80%, where other nodes are running at around 60. So what are the factors contribute to the extra CPU utilization?
I think in this case, I was running a load test, right? And I think the load test, you're seeing some lowered CPU utilization just because of, like I mentioned, these are 3 different zones. And so the zone that I'm running the load tests in probably has a higher latency to that zone, and that zone isn't being fully utilized because there's a higher round trip time. But I think that's
I noticed
probably,
that when you're running the migration, well, you're also having like around 5K get and sets.
oh, okay, that was not the atomic slot migration one, but you meant like the yeah. So I guess I can run it again. This is with no traffic, right? It definitely, I think we were probably seeing the load test before, but like the old slot migration doesn't fully utilize the CPU of those nodes, right? But it adds like about 40% on the importing node and 20% on the migrating node. Yeah.
Oh, okay. What about the atomic migration?
Well, now I have to wait for this one to finish because, but
Okay.
yeah, that's another thing, I guess, a quick note. We have 2 slot migration mechanisms, right? So if you're running like the legacy flow or you're running the new flow, the other one gets blocked for simplicity. Otherwise, it's very complicated to think through the state machine. So in this case, like I've started the legacy one. If I try to start the atomic one, it's going to give me a failure. I could stop this and get it to a stable state and then do it. But yeah, just if you're operating, you might notice that.
Thank you, everybody, for coming. Again, folks are playing bingo, folks are going to talk outside, but thank you, Dr. Zhang.
Okay.
Yeah, everybody's welcome to the bingo. My name is I think security will kick us out.
I think at 7:30. They will kick us out. Well, I think at 7 we're supposed to wrap up. No, I think at 7 we're supposed to wrap up. Yeah. That's like a hard, like, we get the boot. Yeah.
Because copy on write.
Well, I don't know. I could run it and let's see. So you want to see? Okay, this is the. No, you're good. So the CPU bump is actually us transferring data, right?
So now we have to use the atomic.
Yeah, so that was the atomic.
Yeah, there is a huge bump.
Yeah, because that's good, right? That means
that's a copy on write or just.
That's just IO. Yeah, that's because we're fully utilizing the CPU to do you know, we're doing like a bulk transfer, right? So it's actually good for us to better utilize the CPU.
Yeah. Another concern is like because the source node is acting as a master, it's doing its own replication. It also accepts the new traffic, and we're doing both. It's also doing the migration. So.
Oh, you mean like?
You
mean like if a replica comes in to synchronize or?
Yeah. I mean the nodes we're doing 3 things. One is serving the new traffic. So the second thing is like the regular replication. Third one is the migration.
Yeah.
So it seems like doing a lot of stuff. How do we make sure the CPU stays there?
Yeah, I mean, we don't throttle the CPU in any way, right? So it'll use as much as it can, and then once it hits 100%, we have scheduler to decide. So yeah.
Yeah, that's not maybe running hot.
Yeah, so you'll run hot, right? I think it's a good idea to start to think about like how we can sync from replicas so that we can reduce. I think that's a great idea, but yeah, for now it's not there. Yeah.
Got it. Are you planning to add some throttling?
Somewhat.
Throttling command or configuration.
Slaughter?
Yeah.
Like to do what?
Slow down a little bit to.
Oh, slow down. Yeah.
Just CPU as say.
Yeah. I think it probably won't be a command, but we'll probably do it in response to conditions. Like it'll be like load shedding, right? Like so we might decide. Yeah, I think we need something. Once you start operating at scale, you need it, right? Like otherwise, you just start failing replication and other stuff, right?
Yeah.
So it's definitely something that's on the agenda. I don't know if it's on the roadmap yet, but we're talking about it. Yeah.
Oh, okay.
Yeah.
Okay. Thank you.
Yeah. What was your name?
Sean. I'm talking about.
Oh, Sean.
Yeah.
Jacob, nice to meet you.
Jacob,
Yeah.
thank you.
Yeah, of course.
Because I think you mentioned that this feature took like 3 years to go from like inception to like actual rollout or something.
Yeah.
Like how much that was like random design versus like I guess like negotiating.
Well, to be honest, yeah, most of that time was sitting with like Redis kind of dragging their feet.
Sure.
And then once we did Valkey, we started work. So that was like 2024 March.
Okay. Yeah. So I think
And then from there, it's some amount of design, some amount of like, this is my daytime, not my daytime job. So some of it was me doing it, in the weekends and stuff. Other was like bottlenecking on review. Like there was periods of time where I was like, I would crank it out, and then it's like 2 weeks later, there's no comments, so there's some process stuff there.
So I guess I was curious as actually a lot. I feel like a lot of stuff's happening. Seems cool. I just want to know because like Reddit says on stream.
Yeah, I mean, I think
like was interested in like.
Yeah, I think also we've gotten more resources. Like more people are interested after the fork, and like a lot more investment from companies like mine. Although I did mention this is like my night job, like I've gotten more of the okay to spend my days doing stuff with the engine and the open source. So yeah, part of that I think too. Hi, Jacob. You want me up?
Yeah,
thank you. Of course. Yes.
We don't use cluster mode, we basically manage clusters.
Yes.
During deployment, adding replicas, letting it sync, and removing the primary.
Yes.
So, right now, what happens is we have a very high write throughput. We run out of memory on the primary.
Yeah, we see it happen all the time.
But that memory is anyway like unused. So we are allocating memory for 5,000 buffers.
Yeah,
we don't
this was kind of like
primary and replica. We allocate the same amount of memory for places.
Yeah, and this is also like part of the problem I mentioned, which is like we've seen it sometimes where it's like I have 32 gigabytes of memory and I'm using 16 gigabytes. For some reason, the replication won't go over 7 because it's like, oh, but I have 1 gigabyte configured here, and it's like now you have to increase that, and right sizing it is so hard because it's like you just kind of want Valkey to like use as much memory as it can up until the limit, and then it's like once you hit the limit, now start making decisions about what you can and can't do, right? But yeah, no, it's not that smart right now.
Yeah, you mentioned that there are real downsides, right? Other than the fact that
yeah, I mean, I think it's just we internally at Google we started rolling out in memory storage at our in the managed service, and we haven't seen any issues so far. So I can give you that operational data. Yeah, with dual channel. We started rolling out dual channel. We haven't seen any issues with it yet. So I can give you just that tidbit about operational. It definitely helps, especially we noted.
I mean, I've calculated because things are utilization by almost like 10%.
Well, and the CPU utilization, but the CPU utilization was something that surprised me, was just like how much better we can utilize the CPU, because forwarding the snapshot through the parent process actually. That extra IO where it takes, you're basically acting like this, and that is taking away from actual traffic,
So we were on Redis 7.0 before,
No.
not much different because they did not mention piping through the parent process.
Oh, I don't.
Or the initial
Yeah, error messaging might have changed, but none of the only major thing is stated behind the dual channel, right?
So it was always like
Yeah, this was always how the Redis worked, was fork and then sending it over. We would like to get rid of the fork syscall. Another thing, like if you probably don't do this, but like if you run like a 500 gigabyte and you're running it very hot. Oh, so you do? Okay, so one problem we noticed was like the actual time, like if you, depending on how much fragmentation you have and all this stuff, doing that fork syscall, like the accounting the Linux kernel needs to do, it could take seconds. Yeah, but the actual fork syscall will just pause the world for like a few seconds, right? And that can also be bad. So we actually, for 9.1, we're looking at forkless. So like another way to do it. I don't know if it will help memory a whole lot, but it's mostly to get rid of this child process and to get rid of the copy on write.
No, the problem with that is we always have to count for that extra memory that's used during deployment. So we restrict our max memory.
Yeah.
Because
it's basically double, right?
Yeah, if we can use, yeah, exactly. It's double buffer. So if we can use it on the replica, then we can allocate that at least or some part of it.
Yeah.
To max memory, not the whole thing.
Yeah, yeah. Totally, yeah. Yeah, I would